Hello, please confirm that you can both see the presentation and hear me.
Yes, sir.
Okay, thank you. So today we begin the discussion on mathematical theory. Today is our fifth lecture. We have finished some basic understanding of the physics concepts part. Let us see now. So our basic purpose will be to understand differential equations, particularly with respect to the physical context, with respect to physical problems that we shall encounter very soon. So first we shall, I mean, I'm not going to talk in about the broad principles or the principles of differential equations in great depth. Rather, I should be talking about basic methods of solving a differential equation by numerical techniques. In order to understand that, we shall first just try to see what is the purpose or what are the salient advantages of a differential equation. So let's see. We'll start with a very simple example, namely the equation of a straight line. You notice that I have written the word integral equation of a straight line, and that is y is equal to mx plus c, where m and c are fixed parameters of the system. Now you take the derivative of this equation. So you take the M and C, of course, have constant values. They are constants of the system, or you should more properly call them fixed parameters of the system. Be a little clear about the difference between parameters and constants. For example, if I give you the force equation of gravity, F is equal to minus G, M1, M2 by R squared, the radial distance r is the independent variable. Force is the dependent variable. They are variables. M1 and M2 can vary from one system to another. For instance, if you're on Earth, the Earth will have a mass, and let's say you are there. So the Earth mass will be M1, your mass will be M2. But then if you look at the solar system, then we should be worrying about the gravity between the sun and the earth. So the sun mass should be m1 and the earth mass would be m2. Like that, it goes on. So parameters are constants for a particular system, but as you go from one system to another, they can change values. For instance, Earth and human being, M1 and M2. So two values, but once set up for the problem, they are fixed. Similarly, Sun and the Earth for the solar system, once set for the problem, they are fixed. But M1 and M2 are, in general, not predetermined. But the gravitational constant G is a universal constant. So G should be properly called a constant. M1 and M2 in the gravity equation should be called the fixed parameters of the problem. Fixed meaning that they have unchanging values, but these parameters can change from one system to another. So when you talk about a straight line, M and C have fixed values. Once determined for a line equation, they are not going to change. They will not change. So that is what we mean. So when you take the derivative of this equation, y is equal to mx plus c, you have dy dx is equal to m. So c will vanish. And then when you take the second derivative of this equation, d2y dx squared will be equal to 0. So this is the differential equation of a straight line, d2y dx squared is equal to 0, and it is free of parameters. Be clear on that point. So basically, this equation is an integral equation, y is equal to mx plus c, and this is a differential equation. You can easily go from the one to the other. Hello, somebody, please mute your mic. You're causing a distraction. So you are going from this representation to this through a process of either differential calculus or integral calculus. Depends on what you have and where you want to go. Uh, so I've written something over here, free of parameters. So basically what you have is that this integral equation can be reduced to a differential equation, and as a result, you are now free of the parameters of the system. So successive derivatives reduce the number of fixed parameters. This implies greater generalization and more universal relevance. What do I mean by that? You see, if I ask you what is the equation of a straight line, if you tell me y is equal to mx plus c, then I shall ask you what is m and what is c. You will also have to be careful enough to provide me the values of m and c. But if you say d2y dx squared is equal to 0, then that question wouldn't arise. So d2y dx squared is equal to 0 will satisfy any straight line. Therefore, this representation is a more general representation. It is more universal, right? And the second thing is that when you write something in terms of a differential equation contains a derivative. Uh, just a minute, I'm sorry. Just a minute. Yes. I hope all of you can hear me clearly. Please confirm once again. I'm sorry. Please confirm.
Yes.
Yes, sir.
Okay. Thank you very much. Okay. So differential equations contain derivatives. And what do derivatives do? Or what do they represent? Derivatives are mathematical devices that capture changes. And when you say changes, basically you are implying something over here written, implying dynamics. And why are we interested in dynamics then? Because the physical world that we see are, is always changing in time. Everything that you see in the physical world is changing in time. You are changing in time. The structure of the world is changing. On different time scales, things are changing. Human life time scale, the time scale of a civilization, the time scale of the life of a species, the time scale of geophysical, geological processes. So different processes have different time scales, right? Some will be of the order of a few days, some will be of the order of some years, months, years, decades, centuries. Geological timescales will, the changes will be visible on the order of millions of years. So you will have to have a clear understanding of timescales necessary. We shall discuss all those things when we properly take up physical problems. But as you can see, time is very important over here because it is through time that things are changing. And you'll be able to capture the changes with the help of, mathematically capture the changes with the help of a derivative. And equations set in terms of derivatives are differential equations. So basically, these are the two fundamental advantages of differential equations, that a differential equation captures changes through a derivative, and a differential equation, by using a derivative, is more free of parameters, fixed parameters, than an integral representation of the same system. And therefore, a differential equation has greater generalization. Let us see how. First, we shall look at this. We consider differential equations to express changes of a dependent variable, x, let us say. It can be, x can be anything, varying through time t. T is clearly time over here. T is the independent variable and x is the dependent variable, and your purpose will be to see how x is behaving through time. And here we come to a familiar page, which I discussed rather cursorily though, in your first laboratory. We shall talk about a differential equation involving a single derivative and a first order derivative, meaning it is just d dt of x, not d2x dt squared. Therefore, if it's first order, you have a first order here. It's an ordinary differential equation. Why ordinary? Because x has dependence on only one variable. Therefore, any derivative that you'll have will be a full derivative d dt, like that, not a partial differential equation. Although we shall, at the very end of the course, if time permits, we shall briefly also have some understanding of partial differential equations. And they are very important in physics. You have already, through your electromagnetic theory, encountered partial differential equations. Two partial differential equations, very famously, you have encountered. One is Laplace's equation, or equivalently, somewhat equivalently, or close by, was Poisson's equation. And the other is the wave equation. As we showed, light was an electromagnetic wave. Anyway, so this has an ordinary derivative, therefore the word ordinary. It's a differential equation because it involves a derivative. It's of the first order because it is just d dt and not something like d2 dt squared. And now look at the word autonomous. The word autonomous on the right hand side means that this derivative that we have written is written as some unknown, some given function of x, I'm sorry, some given function of x. That is the representation. So this is, we understood, this you should understand is first order autonomous differential equation of first, any system, physical system given expressed by this differential equation, an equation of this form is called a first order autonomous system. We shall look at physical cases later. For the time being, let us just familiarize ourselves with the mathematics part. Here we are. So first is, our purpose will be to solve for x as a function of t, either by hand, performing school level integration, or if that does not work out, then numerically using a calculator and pen and paper, or slightly more advanced using a computer, which you shall do in the lab or whatever. Now you notice something, that I have written something over here. You need an initial condition. Let us go back to the previous page. If you look at this differential equation, d2y dx squared, it was a second order differential equation. And when we wrote its full integral solution, which is y is equal to mx plus c, this introduced two fixed parameters. Now, you can't just let the system dangle with two free parameters without defining the parameter values. So you will have to fix the fixed parameters or determine the parameters with the help of some conditions. Let us see what kind of conditions I've said. I mean, otherwise, your equation will convey no message. So you'll have to provide numerical values to these constants m and c. Suppose I give you a condition. X is equal to 0, y is equal to 0. So you'll put 0 is equal to m into 0 plus c. Therefore, c will be equal to 0. So c has a value now and goes away. C is equal to 0. Then I say the next condition is x is equal to 1, y is equal to 1. So 1 will be equal to 1, m into 1 plus 0. 0 is not participating. So 1 is equal to m into 1. Therefore, m is equal to 1. C is equal to 0, m is equal to 1. From two conditions, you have been able to find the values, the numerical values of the two fixed parameters. Basically, then would have had to provide you two conditions. Otherwise, information would be incomplete. Because you have got a second order differential equation, you must need two conditions. The integral solution will introduce that many fixed parameters, and therefore you must need two conditions to fix the values of those parameters. And so it is that here we are dealing with a first order differential equation. Therefore, we have to prescribe a condition in the variable t for the variable, independent variable t for the dependent variable x. Now I've used the word initial. Why initial? Because t is time. So at the start, initial means at the start. At the start, what was the value of x? So when you say at the start, that is that is to say t is equal to 0. Just you start your stopwatch or anything, you start your process, whatever, and then you start at t equal to 0 and you say that the system or the variable, dependent variable, has a certain value, x naught. And then the system starts evolving through time and x keeps changing. That we shall have to find now. But suppose, as I said, I mean, you ideally you would be able to integrate, you would rather integrate this thing by pen and paper. But that may not always happen. Therefore, you may also have to do it numerically. Let us see now. How do we go about our business? First, I believe you're familiar with this process of carrying out a Taylor expansion of x t about the initial condition t is equal to t naught, t naught. So x is equal to x at t naught, which is equal to x naught, plus first derivative d dt of x at t naught, t minus t naught, plus 1 by factorial 2 d2x dt squared at t naught, t minus t naught squared. Then 1 by factorial 3 d3x dt cube t naught, t minus t naught cube, and then you can go up to infinite orders. I mean, there is no end to this thing, higher orders. The question is that you will have to do this thing numerically. So then you will have to make a choice, right? Up to what order should you go? In the first lab, I mentioned to you that whenever you do a numerical integration, you always have to carry out an analysis first, optimizing between uh, the efficiency of your code, efficiency as in how quickly is your code giving a result. By code, I mean a program, efficiency of your program. Whatever language you are familiar with, I told you, I'm making no restriction on that. Python, C, MATLAB. But I would prefer that you work with respectable languages like Python and C, probably. I mean, MATLAB is a built-in thing. You are programmers and you should be developing everything from the scratch. That's the best way to learn programming. MATLAB has got a whole lot of inbuilt libraries. That has a certain advantage, spares you the effort, but you don't learn coding too well that way. I mean, too very well that way. Let me put it that way. Anyway, so you have to optimize between the efficiency of your program and the accuracy of your program. So the question is that if you want higher accuracy, you can go to as many orders as you want to. But then the process also has to be efficient. So eventually you'll have to optimize it somewhere. I will touch on this very important point of programming in due course. Uh, but anyway, so scientific programming at least. So now let us see, what do we do? So now if you look at the right hand side gives you everything as x as a function of t. I would rather prefer to write this right hand side because fx is known. I don't know x as a function of t beforehand. I hope you are able to understand the subtle point. You have been given a differential equation which you can't integrate by hand, by your basic fundamental integral calculus method. It's a complicated differential equation, let us say. And yet you will have to fix the values of this dx dt at d2x dt squared. How do you take the derivative of x with respect to t, first order, second order, third order, if you don't know how x depends on t by in terms of an algebraic formula? That's a rather tricky point. So you would rather convert, but this thing is given to you. Fx is given to you. Then you would rather convert all of this to fx. Let us see how. You have been given dx dt is equal to fx. So dx dt at t is equal to t naught is fx naught. At t is equal to t naught, x is equal to x naught. That is the initial condition. Now, what about the second derivative of x with respect to time? d2x dt squared. d2x dt squared is equal to, now, dx dt is equal to f. Therefore, d2x dt squared will be equal to df dt. No challenge, I hope. Dx dt is equal to f, therefore d2x dt squared is equal to df dt. Fine. Then you apply chain rule of calculus. You write df dt as df dx into dx dt. Okay. And then you write dx dt as f as given over here. So it is f into df dx. So d2x dt squared is f dx df dx. This you will substitute over here. d2x dt squared at t naught is equal to f df dx x naught. This has a certain advantage now because f is prescribed. The formula of f is given to you. If it is given to you, then you can take a derivative of f as a function of x being known. You can take the derivative of it, df dx. Okay, fine. What about the third order derivative? You will see for yourselves that as we go to higher and higher orders of x versus t, x as derivatives of x with respect to t, the corresponding formula involving f will become more complicated. I shall not go beyond the third order. I've just told you first order is very simple. Second order, slightly working around. Third order, a bit of a working around. Let us see now. d3x dt cubed is what? ddt of d2x dt squared. Okay. And then by chain rule, I'm writing ddt as ddx into dx dt. And this d2x dt squared, I'm writing as fdx. Okay. And dx dt is equal to f. So, excuse me. So basically, I'm writing all the derivatives of x with respect to t of any order in an autonomous form. What do I mean by an autonomous form? Without the involvement of time. Time is the independent variable of the system, but f or derivatives of f should not contain time. So that way I will have the advantage of knowing what these derivatives are. Right. So let us see about the third derivative. Dx dt is f. Fine. So now here you have no presence of explicit presence of time. Time is implicit. What do I mean by time is implicit? Of course, x depends on time, but it does not explicitly appear. So there is no explicit presence of time in this thing. So d3x dt cubed therefore will be equal to, let's look at this formula. F is out here, then let's go inside the square bracket. ddx of f df dx. ddx of f, first, I mean, just product quantity is taking the derivative of that. So df dx into df dx will be df dx squared plus f into d2f dx squared. This is just basic calculus that we are doing. So f df dx whole squared plus f squared d2f dx squared. As you can see, the third thing required some workout. So d3x dt cubed at t naught is equal to f df dx whole squared plus f2 d2f dx squared at x naught. So as soon as I eliminate t explicitly, then we'll have to prescribe everything in terms of the value x naught, right? So that is how it is. Next task will be in this equation that we have got over here. They are equivalent. This and this are equivalent. In this equation, we substitute all the derivatives of x of whatever order, in this case, 3 orders. You can very well imagine if we wanted to go to the 4th order, you can amuse yourself by doing this exercise. But I hope that I have at least conveyed the principle of how you convert the derivatives of x as they change with t to the autonomous form of derivatives of f as they change with x, right? So that's so you can do it for any orders if you want to. The only problem is that the algebraic work will become pages and pages long for as you go to higher and higher orders. So 3rd order is enough for us. For your laboratory work, you have already started with Euler. You will at most have to go up to the 2nd order. Only extremely rarely, I can't think of any instance so far, you may be asked to go up to the 3rd order. So basically, this is the formula that you have to look at. I'll also provide you a supplementary set of formula with some errors in these notes that you will see soon enough. Anyway, so you can see now, except for t minus t naught, which is the step size, all the other things are in the autonomous form. There is no explicit presence of time in any of the other things except for the step size t minus t naught. You start at t equal to t naught. Then you take a step, which is going to t, the next value of t. Okay, let us go back to our original Taylor function. That's the more familiar thing with which we are comfortable. We will look at this equation now and see what we will do. We will take x naught to the left-hand side. So it will be x minus x naught. Then we will divide this equation throughout by t minus t naught. When we do that, this is from the Taylor expansion, that's this previous. So we have taken x naught to the left-hand side, and then we divide throughout by t minus t naught. All the terms have a t minus t naught of some order. So first, x minus x naught by t minus t naught. What is x minus x naught? It is delta x. A small difference in x divided by t minus t naught is a small difference in t. Well, small or large, it doesn't matter. Difference in x, difference in t. Okay. And then on the right-hand side, what have we got? dx dt t naught at t naught, half d2x dt squared at t naught, t minus t naught, 1 by 6. 1 by 6, where is 1 by 6 coming from? Because it is factorial 3. 3 into 2 into 1. This is 2 into 1. So 3 into 2 into 1 is 1 by 6. I hope you have understood that point. So 1 by 6 d3x dt cubed t naught, t minus t naught squared. And then you go. Okay. Now you will substitute all of these things, all these non-autonomous form, x, the derivatives of x with t of any order with the derivatives of f with x. So you can see now you have autonomous forms on the right-hand side in the step size. Now the next thing, I said that this is a difference in x divided by a difference in t, right? Difference in x divided by a difference in t. Now you make the difference go to infinitesimally small value. What do I mean by infinitesimally small value? Basic school level calculus. What is that? It is that, you see, between 2 points, any 2 points, you have an infinite number of points. That's what we learn, because a point is a zero-dimensional object, and if you're tracing a line out by dragging a point across, you take a point and you trace the point through space. What will it leave behind? Uh, if you trace it on a straight track, it'll leave behind a straight line trail. If you make it go on a circular path, it will leave behind a circular trail. So that is what it is. So basically, but the straight line trail accommodates infinite number of points, howsoever small the straight line may be, right? So when you say infinitesimal calculus, you are basically, so basically any 2 points between the two of them will have infinite number of points. But when you say things have gone to infinitesimally small, it is as if you're saying that you have one point and then you have the next point, and between the two of them there is no other point. So it's as if you've reached two adjacent points side by side. But that's a slightly complicated concept, really. However, in physics, I have already mentioned to you the possibility of the Planck length. Maybe that will serve as it is, but then physics is not math, and math is not entirely, I mean, they are not entirely each other. Anyway, so that is what we have to do now. Delta x by delta t, right? Sorry, just a minute. Yes, delta x by delta t. Um, when t goes to t naught, that is to say these two things are almost zero, infinitesimally small, but not exactly zero. Delta x by delta t could be written as ddt of x. I have made an error over here. It should be x, ddt of x, and ddt of x when t goes to t naught is equal to fx naught. You just make a, how you follow this subtle point a little carefully. When I say delta x by delta t, I imply, follow this point extremely carefully, everybody. It's about it's a conceptual point. When I say delta x by delta t, I imply one number, namely delta x, whose value is x minus x naught, divided by another number, namely delta t, which is equal to t minus t naught. One number on top of another number. When I say dx dt, as written over here, dx dt, I should have written dx dt over here, but I'll give you the correction state also. When I say dx dt, I don't mean that. Note, I did not say dx by dt. I have said delta x by delta t. Delta x by delta t is one number on top of another, one number divided by another. But when I say ddt of x or dx dt, I do not mean dx divided by dt, although we tend to think like that and we work like that. But no, you should rather see it as an operator ddt acting on x, or operator ddt acting on f. I mean, this is a mistake, as I said. I'm sorry about that. The operator ddt acting on x. There is no such thing as dx. What is dx? It's as if that the separation between 2 points with nothing in between, but that doesn't happen geometrically. Between any 2 points, howsoever close they may be, there will be an infinite number of points. Otherwise, all of your concept of the number line comes crashing down. And yet in calculus, we do that. As if when we say infinitesimal calculus, we say we have gone to this one point, beyond which there is the next point, and in between there is nothing. So that is not the difference between 2 points. That's and something like an operator. So you write it as ddt. You should talk of it as ddt. So this is this divided by this, and whereas this is this operating on this, and that's equal to fx naught. At t equal to t naught, x is equal to x naught. So what we do now is this: that in the Taylor expansion, keeping only the first order, when this thing becomes very small, when t is equal to t naught, that is to say your t is nearly equal to t naught, when your step size is very small. Let us see. When your step size is very small, look at this equation. T minus t naught will be a very small number. T minus t naught squared will be an even smaller number. Right. Why? I have been saying this thing again and again. If a number is less than 1, between 0 and 1, and if a number is greater than 1, then there will be a serious difference between their higher powers. First, you consider a number greater than 1. 2 is a number greater than 1. What is the square of 2? Higher power of 2, next higher power is a square power. So 2 squared will give you 4. Now you go between 0 and 1, less than 1, so 1 by 2, a small number compared to 1. We square 1 by 2, what will you get? 1 by 4. 1 by 2 is 0.5, 1 by 4 is 0.25. So if a number is very small, let's say 10 raised to minus 5, immediately you square it and you'll get 10 raised to minus 10. So 10 raised to minus 10 can be safely neglected against 10 raised to minus 5. That is the whole idea. So when your step size is small enough, when t goes to t naught but not exactly equal to this, you can write this thing as this approximate formula, which we have discussed in this thing. X is equal to x naught, as in this formula, is equal to f x naught at t minus t naught. You have neglected this order, you have neglected this order because t minus t naught is a small number. So this is the Euler formula, the forward Euler formula. What is the meaning of the word forward? Euler, of course, is the famous Swiss-Russian mathematician Euler. He lived 300 years ago, by the way, so there was no computer at that time. He did all these things numerically by hand, which today you will be doing by your computer or calculator. But the principle holds, right? So forward, what do we mean by forward? Here is this thing. Graphically, let us try to understand the meaning of the word forward. You start at t equal to t naught at, and for which your initial value of x is x naught. T equal to t naught, x is equal to x naught. A basic step size has been prescribed to you, which is delta t. In your, if you have to work by hand, it will be 0.1. If you have to work by the computer, it will be 0.01, whatever it is. So t is equal to t naught, then delta t. And the delta t is a fixed step size. So when you add delta t to t naught, you move forward in time to the value t1, right? Why don't you look at this equation? X is equal to x naught plus f x naught t minus t naught. Now f x naught is a constant quantity because you are just taking the value of x naught, which is a fixed value, and putting it here. Therefore, f x naught is a constant quantity, right? X naught is a fixed constant, is a fixed number, and you're just taking the function of that fixed number. So this is constant. Basically, this equation is the equation of a straight line. I hope that you have followed that fact, all of you. What do I mean by equation of a straight line? I can write the equation of a straight line, just think in terms of yx. Perhaps that will help you understand. Y is equal to constant plus m into x minus another constant. And this constant and this constant will absorb into each other, and you'll have an equation like y is equal to m into t is x now, plus c, where c is x naught plus fx naught minus into minus t naught. This is the equation of a straight line. So now you follow carefully. Uh, you start at t naught and with the value x naught, go a step size delta t, find the value of the new quantity x1 at t1. This is what you shall get. However, now you note something. If you have any doubt or anything, clarify. Maybe now, or maybe by writing a note in the chat, a question in the chat, or maybe at the end of the chat, end of the class, whatever it is, but be clear about that. The actual function of xt will be going along this track, just to give you a schematic representation, but you have fallen short of the function. Why have you fallen short of the function? Because you're treating this fx naught business as a constant slope of a straight line, but it is not a constant slope. If you think about it, this equation that you have is like fx is like the slope of the function x as it depends on t, except that this slope is not the slope of a straight line, but it's a variable slope. A straight line has got a constant slope, right? So if f were to be constant, x would have been equal to f into t. Very simple thing, right? But f need not be a constant. Therefore, the actual function will change, let's say, along this track, actual value. But you have taken only a straight line approximation of the actual function, and therefore you've fallen short. So here you have error at first step. Now you have come over here. Okay, what do? You take the second iteration. What is the second iteration? You start with the value of t1 at t1. You start with the value of x1. Then again you add delta t to t1. It will take you to t2. And what is t2? So here you start with t naught, t1, x naught, x1. Then you go to T1, T2, X1, X1, X2. So like that you go. So now you can see, meanwhile, the function has gone even more beyond. What is happening over here? You are taking lesser value of the so-called slope, which should be a variable, but you are taking a straight line slope. However, this is not completely a universal straight line. Had it been a universal straight line, you would have started over here and you would have gone along this track and gone straight this way. But instead of doing that, you are breaking the straight line, and in every step size, you are taking a straight line with a slightly higher slope than the previous one. This has got a lower slope compared to this one. I hope you're following that subtle point. But anyway, I've mentioned something over here. Error at the second step, more error than at the first step. This is the error at the second step. This is the error at the first step. And you can see that the error at the second step is more than at the first step. Whereas the actual value of the function is this point and this point, actual value. So this is the basic principle of the Euler method. How do you go about the Euler method? It's a very simple thing. Don't even worry about all this talk. I just ask you to integrate dx, going from xn to xn plus 1, right? And then what you do, by chain rule, you write dx dt. Loosely, you also say dx by dt. Actually, we are thinking like that. But one should not say dx by dt. Dx and dt are not small numbers, right? So you rather should say ddt of x, or maybe dx dt, whatever. So dx dt into dt, as if these two things cancel like numbers, but once again, they should not be thought of as that way. And this integral on the left hand side is not very difficult. Integral dx, the integral and d will cancel, and you will have, with the definite limits, xn plus 1 minus xn. Okay, now what have we got on the right hand side? On the right hand side, dx dt is fx, that into dt, then going from tn to tn plus 1, because the integral is now over t, so you have to put the time limits accordingly. Now what you are doing over here is that you are treating, suppose you follow this point carefully, suppose fx were to be a constant quantity, then what do? You can take the constant out of the integral, you take it out of the integral, and then you can write fx into integral dt, which would give you just integral, and d will cancel, and it will give you tn minus 1 minus tn. So that I will write as delta t. So the whole point of integrating by the Euler method, this is integrating by the Euler method, where we have treated fx to be almost a constant, as if it is a constant, not almost, as if it is a constant, and we have taken it out of the integral, and taking it out of the integral, and then this thing I'm writing as t with the two limits, tn plus 1 minus tn, which is delta t. Delta t is equal to tn plus 1 minus tn. Delta t time steps all equal. Now you can very well imagine, if I were to ask you, you follow this point carefully once again, if I were to ask you to integrate a straight line, fx is universally not a constant quantity, it is a function of x. But suppose fx were to be a constant, then you just have a straight line. If that were to be so, then this approximation of bringing f out of the integral will be exact. It's not an approximation. Therefore, if f is a constant, not a variable, the Euler method is exact. But in most cases, the f that you will get is not a constant. So particularly in complicated physical problems, they will not be, but you'll see for yourselves. Anyway, that is the, that is the basic principle of the Euler method. Just take a function, treat, what is the whole idea? You have been given this autonomous function. Within a time step of delta t, you treat f to be a constant quantity whose value will depend on the value of x at the start of the time step. What do I mean by that? Here, at the start of the time step, t naught, the value of x is x naught. So this thing, you treat f is just a function of x naught. Here, at t equal to t1, x is equal to x1. F will be just a function of x1 for this whole band. So it will be a higher, have a higher slope than this thing. It could also have a lower slope. If the function were going down, you'll have a lower slope. So as I said, if fx is not constant, then the Euler method gives errors in the numerical calculation, as I have drawn in this diagram. I mean, that's a simplistic diagram, but you can also have more complicated cases in other contexts. So we shall see about that. We have already discussed this thing, but I'll touch on this whole business of errors over here. That is, we have discussed this thing in the class, in the lab, I'm sorry. So example, dx dt is equal to fx is equal to minus x. Initial condition at t equal to 0, x is equal to 1. That is the initial condition. Okay, you can integrate by hand. This is not a challenge. Integrating by hand is a very simple exercise for this particular problem, but not always. So the integral solution, you separate variables, you take x to the left-hand side, dx by x is equal to minus dt, integrate, and you'll get log x is equal to minus t plus a constant, which you write as log c. And so x is equal to c into e minus t, e raised to minus t. And when t is equal to 0, x is equal to 1, you put t equal to 0, e raised to 0 is 1. X is equal to 1, this is 1. Therefore, c is equal to 1. Hence, x is equal to e raised to minus t. That is the exact solution. Okay, fine. Now you will have to do this thing numerically by hand, I mean by calculator and pen and paper. And then if you reduce the step size, you will have to do the tedious task on your computer. So what have we done over here? We are taking delta x, which is xn plus 1 minus xn, and then we're taking the xn to the left-hand side, is equal to f into delta t, dt is delta t, fxn is here. Now fx is equal to minus x, so we write x subscript n plus 1 is equal to xn, fxn is equal to minus x, so there is minus xn delta t. Okay. I've just taken a very simple example. Delta t is equal to 0.1, x naught is equal to 1. You will start with x equal to 0 and go forward in time, right? Forward Euler. That is it. So basically, you're starting with a small value of t and then you're going to larger and larger step sizes. So there's a forward Euler method. You're going forward, starting with something. So x1 is equal to x naught minus x naught into delta t, and x naught is equal to 1, delta t is equal to 0.1, so 1 minus 1 into 0.1 is 0.9. x2 is equal to x1 minus x1 delta t. So as soon as you've got the value of x1, next iteration will be, so you start with 0 here, and 0 plus 1 is 1. Next is, you've got 1 here, it goes now to the right-hand side. This is just setting a loop in your program, right? Python, C, whatever, MATLAB. So this will be 1, this will be 1, and this will be 2. So x2 is equal to x1 minus x1 delta t. X2 is 0.1 minus 0.9 into 0.1 is equal to 0.81. So exact values of x will be, by this exact integral solution, will be x1 is equal to e raised to minus 0.1. X naught is equal to e raised to 0. X1 will be e raised to 0 plus 0.1, the step size, e raised to 0.1, e raised to minus 0.1, I'm sorry, minus 0.1. So that is 0.9048. Then another 0.1 step size, e raised to minus 0.2, x2. x2 is equal to 0.187. So you can see your simple Euler formula. This is actually an exponential decay function, right? So this is something like an exponential growth. A decay would go down like that. This is an exponential decay function, but you are matching it with a series of piecewise straight lines. This is a function, and you're matching that function with a series of piecewise straight lines. And so here also you're doing the same thing. This decay function, you're matching with a series of piecewise straight lines. And at every step, you are introducing some errors. The error, in this case, percentage error calculation, by the way, is very important. Many of you make mistakes. Always remember, percentage error in the denominator, you should have the exact value. And in the numerator, first the numerical value, second the exact value. So numerical value minus exact value by exact value, right? That's how you should do it. So 0.9 minus of 0.9048, 0.9048 is minus 0.5%. At x2, numerical value minus exact value by exact value. Just remember that thing. People tend to mix up this or that and get wrong percentage errors, and you'll be asked in the examination, you'll be asked to find percentage errors, right? So it's again a negative value. So what do I mean by that? It means that this minus this is a negative. This is the numerical value. This is the exact value. The numerical value is less than the exact value. So this is the same thing that is happening over here also. The numerical value is less than the exact value. So the negative sign implies falling short of actual values. By the way, the reverse is also true. The function may be going down faster than your numerical algorithm. As a result, your numerical values can be more than the actual function value, in which case you'll have a positive error, right? So that is how you should, I mean, don't do, I mean, it doesn't always have to be that percentage errors will be negative, that you'll be falling short of the exact value. You can also go higher than the exact value. And how can that happen? Just think of something. Here I have drawn a function which is concave upwards. I hope you're following, right? When you draw a straight line slope is a tangent at this point t naught x naught, and the tangent will be below the function. But suppose concave upward, by the way, what is the second derivative of a straight line? No challenge. Second derivative of a straight line is 0. Second derivative of a concave upward function is a positive number. Second derivative of a concave downward function is a negative number, meaning if you have a function going like this downwards, the straight line will be above that. Like, let's say, I don't know, you have an inverted parabola and your straight line will be above that. In that case, your errors will be positive. Percentage errors will be positive number. The straight line will be above the function. In this case, the straight line is below the function, so the function is concave upwards. So that's something similar that is happening. You don't have to worry about what is the nature of the function, but just follow the processes properly. Follow the processes properly. Incidentally, you can ask me, how will I know the percentage error if I do not know the exact value? Yes, very good question, in which case you will also have to integrate and find the exact solution and match it with the numerical value. But sometimes the function may not be integrable by hand as you have done over here. In that case, the question of finding the percentage error doesn't arise. The percentage error should always be calculated knowing the exact analytical value. Analytical as in by a proper pen paper analysis as we have done here. So yeah, so with that, I have hope I have conveyed you enough idea about these functions. Now you should be able to work on your numerical work lab sheet, which we shall have on Monday. But there are, I mean, in the class we discussed the first two questions. There were also four other questions. Let us discuss the principle of those four other questions here. First order linear autonomous systems. Let us see how we go about this thing. First order, ddt of x. Autonomous, the right hand side is just a function of x. Linear, what do I mean by linear? The right hand side is just a linear function of x, as in mx plus c or ax plus b. Here I have just written plus minus ax. Plus b, if you had written, it would have. This function, if this function f of x, this function f of x, this incidentally is a linear. You can see it's just a function of x. Linear meaning equation of a straight line in the form of mx plus c. Right, that's the most general equation of a straight line. Here m is equal to -1 and c is equal to 0. That is how you should see it. Okay, so I have got this thing plus minus ax. Here also, as I said, I mean, it will be in the form of mx plus c, as in y is equal to mx plus c. But instead of y, I have taken the derivative. So x as a function of t is not a straight line. It is just that the autonomous function is in the form of a straight line. Fx is in the form of a straight line. Otherwise, the function itself, we will see what happens. Right, so be very clear. When we say linear equation, linear differential equation is different from the equation of a straight line. This is the equation of a straight line. Yes, sorry, this is the equation of a straight line. But when I say dx dt is equal to ax plus b, the outcome will not be a straight line solution. We just say that the differential equation dx dt has a linear form, linear autonomous form. Okay. I'm just introducing a few things. rescaling. Here we have got this A business here. So we would rather not have that A thing. So what do we do is that A is a constant and A is a positive number, right? A positive constant. So we take the A to the left hand side and we write dx d of at. A being a constant, it can enter a derivative, come out of a derivative, enter an integral, come out of an integral, whatever. So we write it as small a into small t is equal to plus minus x, right? And then we rescale the time as capital T is equal to AT. What do I mean by rescale the time? Earlier, your unit of time, your time was T. Now you are rescaling it to A times T. Let's say earlier your time was 1 second in unit of 1 second. And suppose A is equal to 60, right? If A is equal to 60, now you have got 60 seconds. And what is 60 seconds? A minute. So basically now, capital T, small t is on a scale of 1 second. Capital T will be on a scale of 1 minute if A is equal to 60. That is what I mean by a rescaling. Right, so you have rescaled the time. So then after that, you can separate the variables. So you have done two basic things over here. First, rescaling, and second, separation of variables with the help of a very simple example. But this thing will extend to more complicated problems in due course. So this, whatever we have done. So x goes to the left-hand side. You have dx by x is equal to plus minus d of capital T. Then we put the integral sign. So dx by x integrated will give you log x is equal to plus minus t. And then you can introduce a constant log a. And plus minus t, plus minus capital T, I'm writing as log of e raised to t. Log of e raised to t is capital T, basically. So this is just a roundabout way. So everything is now in the log form. And so when t is equal to 0, this will be equal to 1. E raised to 0 will be 1. Log of 1 will be 0. And x is equal to x naught. If x is equal to x naught, log of a will be equal to log x naught. Therefore, capital A will be equal to x naught. So when t is equal to 0, x is equal to x naught, and x is equal to x naught, e raised to plus minus at. For the exponential growth, x naught is not equal to 0. That is a very important point, by the way. I'll just briefly mention what I mean by that. But first, let us just look at this thing, equation. You see here, you start with x naught. If you have the plus sign over here, a is always positive, right? Or in this case, I've actually made I mean, a is always positive here. So when you have plus at, you'll have a growth over here. And when you have minus a, with a being positive, you'll have a decay. I made a mistake over here. It should be a is positive. So minus a is positive, and sorry, minus a is negative. So maybe I should put a minus sign over here. Minus a is a negative number with a being positive. Minus a is negative. This is a decay. Now, I just should mention something that when you have these, this is an exponential growth when you have the plus sign, and when you have a minus sign, this is an exponential decay, right? So if this exponential decay and exponential growth, you'll have a plus or a minus. But in both cases, it is starting with x equal to x naught, which is non-zero. If x naught is not equal to, if x naught is equal to 0, then you'll have a bit of a problem. Can't you see what the problem will be? Just look at your numerical exercise. Suppose x naught is equal to 0. You'll have 0 minus 0 into delta t, which is equal to 0.1. x1 will be equal to 0. So x1 will be equal to 0. So you'll put a 0 over here, you'll put a 0 over here, and delta t will be equal to, again, 0.1. So 0 minus 0 into, what will happen if you start at x naught is equal to 0? Your system will never grow. 0 minus 0 into 0, so x1 will be 0. As soon as x1 is equal to 0, x2 will be 0, x2 will be 0, x3 will be 0. So you can keep increasing in time. Through all your time steps, the next iterated value of x will be equal to 0. Why do you think that is happening? Simple answer, when you say at initially x is equal to 0, dx dt will also be equal to 0. And what is dx dt? Dx dt is the rate of growth. Like I told you, you have to specify the growth rate also. Your initial value is 0. Your growth rate is 0 because of this equation. Initial value, instead of x equal to x at t equal to 0 or 1 is equal to 1, you write x at 0 is equal to 0. Initial value is 0. And then your growth rate is also 0. So you have got nothing to start with, and therefore you're going nowhere either. As a result, continuously, you'll just be returning 0. So be very careful about that particular point. As soon as you have an exponential kind of a situation, if you have a plus sign, you have exponential growth. If you have a minus sign, you have exponential decay. Whatever you do, you have to be very careful that the initial value must not be 0. If it is 0, then you're going nowhere. Why do you think that is happening? Because this is the equation that is growing in a geometric form. I hope you are aware of two kinds of progression. One is arithmetic progression and the other is geometric progression. In the arithmetic progression, you start with a certain value and then you keep adding constant values to that and grow. Whereas in geometric progression, you start with a certain value and then you have a product of that value as in your subsequent steps. So if you start with a 0, then whatever you product you can put in, anything multiplied with 0 will always turn out to be 0. Right? So that is the problem over there. Exponential growths follow geometric progression. That is why you must be careful. If you are starting with an arithmetic progression, then you can very well write initial value is 0. But when you're starting with a geometric, when you're following a geometric path, geometric progression, then your initial value must not be 0. So for exponential growth, x naught is not equal to 0. Growth or decay, whatever. Uh, Anyways, I'll make a correction over here. Just please make a mental note of that point I've stressed upon. Now we consider a more general expression. So we had a plus minus ax. Now we will have a more general expression of fx, dx dt is equal to fx, a plus minus bx. By the way, later when you do radioactive decay, this equation will be very important. Dx dt is equal to minus ax, decay. You start with an initial value of a certain radioactive element, and then as time grows, it goes on decaying, right? So please make a note of that. Now let's have a slightly more involved discussion. Dx dt is equal to fx in a more general linear form, a plus minus bx, where both a and b are positive quantities. Consider the negative sign first. The negative sign here will be dx dt is equal to a minus bx. So what we do is that we shall have to rescale this equation as before. Note what we have done here. What we did was to rescale the equation and separate the variables, right? So we are doing the same thing over here. We are rescaling this equation and separating the variables. And the principle is still the same, except that the system has become slightly more complicated. So dx dt is equal to a minus bx. So what do? You divide throughout by a. I'm sorry, throughout by b. So you'll have a by b minus bx. Then when you've divided throughout by b, this b goes to the left-hand side as well. So you have got b being a constant, it goes inside the function, inside the derivative, and d of bt. Again, you rescale, you have now got two things. T can be rescaled to be b times small t. Small t can be rescaled to be capital T with the factor of b. Capital T is equal to bt. And we are defining a new quantity x naught, which is equal to a by b. Right? When you have this thing, we can then again rescale by x naught. Let us try to see how. So capital T is equal to bt. So this thing here, d of capital T, so it will be dx dt, d small x, d capital T is equal to a by b is x naught minus x. Okay. Next thing that we do is that we divide throughout by x naught. So it will be, again, it's a constant quantity because a and b are constant quantities. So when you divide throughout by x naught, you'll have small x by x naught. So it will be d capital X dt is equal to 1 minus small x by x naught, which is again a capital X. What have we done? By this whole exercise, we have made our equation free of parameters. That's an advantage. What advantage? When you want to integrate by hand, Having to worry about adjusting for these parameters is a pesky business. Also, when you are going to do, when you work on a computer, if you can reduce your parameters by a little algebraic adjustment before you feed your formula in the computer program, that will be helpful for the program efficiency as well. So maybe your final answer, you can reconvert everything in terms of the parameters, but when you make the loop and all those things go round, if the loop wouldn't have to work with all these parameters, it will run that much more efficiently, faster. So better that you fix the values of the parameters, define the parameters at the start of the equation, then once you get the final result, then you can again rescale back to the old parameters. But the main function subroutine and all those things should be free of the parameters. That will help your programming efficiency. So just make a note of these things as you go along. A little bit of, I mean, programming doesn't always have to be only on the computer. It should also happen a little bit on your notebook. Thereafter, you can feed everything in your computer. This will, these are just, I mean, this is, of course, a very trivial thing, A and B. So the computer will, I mean, you will not feel the difference in time at all, even if you were to have introduced all these parameters. But the possibility may arise in more complicated instances. Anyway, so now what we shall do is we shall separate variables. We will take this 1 minus x thing to the left-hand side. It will be d capital X by 1 minus x. Integral is equal to integral d capital T by separating variables. Okay, fine. So what do I mean by separating variables? All x's are on one side, all t's are on the other. Now, you notice that I'm doing a slight trick over here. I'm not writing x minus 1. I'm rather writing a minus x here and a minus t over here. And so this variable over which this left-hand side of the integral equation, left-hand integral is to be worked on is minus x. So basically d of minus x divided by 1 minus x. And so that should be log of 1 minus x, this thing. And this is equal to minus dt. Minus dt is minus t, but that I'm writing as log of e raised to minus capital T, and then the constant I'm writing as log as well. So log of 1 minus x is equal to log x naught into e raised to minus t. Okay. And so basically, this is the final solution. 1 minus x is equal to x naught e raised to minus t. If that is so, then the initial condition t is equal to 0. Now you notice something. I'm not saying that x is not equal to 0 at t equal to 0. I'm saying x is equal to 0 at t equal to 0. Let's see why. Because just a while ago I told you if you have to worry with exponential functions, you shall have to worry about what kind of initial condition you put in. Otherwise, your function will not grow at all. We shall discuss those things in detail soon. Okay, so here we are, x equal to 0. So when so for t is equal to 0, this is another error, but it is there in your correction sheet. This is equal to 0. This for t is equal to 0. We have, this is not greater than 0. For t is equal to 0, we have 1 minus 0. So when small t is equal to 0, capital T is also equal to 0. When small x is equal to 0, capital X is also equal to 0. How so? Small t is equal to 0, capital T will be 0 because b is a non-zero constant. When small x is equal to 0, capital X will also be equal to 0 because small x is just being divided by a constant number, non-zero number. So there we have 1 minus 0 is equal to x naught into e raised to 0, which will be 1. So 1 minus 0 will be equal to x naught, and x naught therefore will be equal to 1. So here we are. X is equal to 1 minus x naught into e raised to minus t, but x naught being equal to 1, your equation of x as an explicit function of t is written over here. Capital X is equal to 1 minus e raised to minus t. Thereafter, you just return to your old variables because ultimately you'll have to work with the scale and parameters which have been provided to you. So capital X is equal to small x by x naught. Therefore, small x is equal to x naught into e raised to minus bt, and x naught therefore will be equal to a by b into 1 minus e raised to minus bt. There you have it. So let's see. Look at this formula. When t is equal to 0, this is the integral solution that you have found after this long exercise. One of your lab work problems or will be using this formula, right? one of your lab work problems will be using this formula. X is equal to so when t is equal to 0, e raised to 0 will be 1. 1 minus 1 will be 0, therefore x will be equal to 0. That's the behavior in the small time limit. Small time limit meaning initial time, that is 0 time. Now let us look at what happens when t goes to infinity. When capital T goes to infinity, small t of course will also go to infinity. So when capital T goes to infinity, look at this formula over here. E raised to minus infinity will be 0. So 1 minus 0, capital X will go to 1. Okay, what about small x? E raised to minus b into infinity minus b into infinity will still be infinity, e raised to minus infinity, so that will be 0. So 1 minus 0 will be equal to 1. So x, small x will be equal to a will go to a by b. So that's the long time limit. Right. So when t goes to 0, x will go to 0. When t goes to infinity, x will go to a by b, or capital X will go to 1. So what we are doing now is to see, basically when you work with your computer, you will be plotting the function as I have showed you. I mean, given you a demonstration with the help of the lab reports of your seniors. When x, I mean, you have to plot the function, but sometimes it would also be good if you have some sense of the plotting by hand. You can do the plot by hand. Let us see. We have a long time limit. We have a short time limit. Now we will see whether the function has a turning point or not. Does the function have a turning point? What is the characteristic of a turning point? Characteristic of a turning point is that the first derivative will be 0 and the second derivative will be non-zero. So we'll take look at the first derivative. We have got x as a function of t. What is the behavior of dx dt? Dx dt is equal to, if you take this thing, it will be e raised to minus t. Dx dt will be 1, or that gives you a 0 derivative, minus of e raised to minus t, taking the derivative of that, minus and minus will be plus, so plus e raised to minus t. Now, plus e raised to minus t from this formula will be 1 minus x, which is the same thing that you have over here. Dx dt is equal to 1 minus x, right? So when t goes to infinity, this thing goes to infinity, dx dt will go to 0, of course, well, because x will go to 1 and dx dt will go to 0. All right. What about the second derivative? You look at this equation. Second derivative, d2x dt squared will be minus of e raised to minus t. When t goes to infinity, d2x dt squared will also go to 0. And that is a particularly important point. You do not have a turning point. At x equal to 1, the function is going towards a limiting value of a by b. For t going to infinity, capital X going to 1, the function x, small x, is going to a limit of a by b. At x equal to 1, the derivative of the function vanishes, dx dt at x equal to 1. As you approach x equal to 1, 1 minus 1 will be 0, dx dt will go to 0. But d2x dt squared will also go to 0. And that is not the signature of a turning point. A turning point must have a first derivative 0, a second derivative non-zero. Incidentally, if the second derivative is a positive number, then you say that it is a stable turning point, a minimum. And if the second derivative is a negative number, you say that it is an unstable turning point, a maximum, something like that. So, but here the second derivative is vanishing. Therefore, there is no turning point at x equal to 1. This falls into a general pattern of autonomous systems. What is it? Let us see. For a first order autonomous system, dx dt is equal to fx. We started with that. Let us look at d2x dt squared. d2x dt squared is equal to df dt. And by chain rule, we write that thing as df dx into dx dt. And dx dt is equal to f. So when dx dt is equal to 0, if look at this formula, when dx dt is equal to 0, this thing is equal to 0, d2x dt squared is also equal to 0. Otherwise, it wouldn't happen. This is a general proof here. You have it. df dx, we don't know what it is. It can be anything. But if dx dt is equal to 0, by the nature of autonomous differential equations, d2x dt squared will also be equal to 0. So both the first and second derivatives vanish at the same time. If the first derivative vanishes, the second derivative must vanish. And that is not the signature of a turning point. Be careful about that. So we don't have a turning point in the function. Therefore, the function must be growing monotonically without twisting or turning. It goes to zero for small time. It goes to a saturation limit in the long time. And somewhere in between, we shall have to see. We shall have to look at the, uh, when t is equal to 0, the function goes to 0. But when t is small but non-zero, then what will the function be? That is the question. When t is small but non-zero. Hello, somebody please mute the mic. I don't know. So somewhere, what do I mean by t is equal to small and non-zero? Here we are. T, capital T is very much less than 1. That makes it small, but it's greater than 0, which makes it non-zero. So your function is e raised to minus t. Here, this time-dependent part, capital X is equal to 1 minus e raised to minus t, right? Sorry, just a minute. I don't know, some disturbance is happening for whatever reason. Okay. So here is another trick that you will do. You write e raised to minus t as an exponential series, 1 minus t plus t squared by factorial. I hope you're aware of this thing. E raised to x is equal to 1 plus x squared by factorial 2 plus x cubed by factorial 3, and like that. But here you have got a minus. So all the odd powers will have the minus sign and the even powers will have the plus sign. Now, x is equal to 1 minus e raised to minus t. So 1 minus of e raised to minus t, we are writing like this, right? Since t is very much less than 1, successive terms in this series will diminish rapidly. T is very much less than 1. I told you, let's say t is 10 raised to minus 3. T squared will be 10 raised to minus 6, 1 out of 10 lakhs. T cubed will be 1 out of 10 raised to minus 9. That is 1 out of 100 crore. So these numbers, the higher orders can be neglected. So successive terms in the series will diminish very quickly. And you can, for t very much less than 1, you can approximate this solution as x is nearly equal to 1 minus of 1 minus t. You just keep this first order term, drop these things, and minus 1 and minus 1 will cancel, and minus will be plus, so x will be equal to t, capital T. X by x naught is equal to bt, capital T is equal to bt, so small x will be equal to a by b into bt. So that will be equal to 80. So the early growth is a linear growth. Let me just quickly just show how you should be plotting this function with all the knowledge that you have acquired. So for t very much greater than 1, t going to infinity, there is a convergence towards x going to 1. And for small time, the early growth is linear. So there will be a transition that takes place between, two kinds of behavior you will have. Between 0 to 1, you will have a straight line behavior, and beyond greater than 1, beyond capital T equal to 1, you will have a convergent behavior. So if you were to plot all of these things, this is how you should see it. Let us see what we have discussed so far. Here you have x plotted along this direction, t plotted along this direction. Capital X or small x doesn't matter, because you can rescale it. Here capital T and small t. When t is equal to 0, x is equal to 0. When t goes to infinity, capital X goes to 1, or small x goes to the value of x naught. That is the terminal value. The linear behavior is not universal, meaning that you have a straight line behavior here, but it doesn't have to keep going like a straight line all through. It can converge, it will converge. Early growth is linear from 0 to roughly about t equal to 1, because this approximation, 0 to less than equal to 1 for capital T, is going to give you a solution that is linear, but this approximation is valid within this band only. So from 0 to t equal to 1, you have got a linear behavior. Beyond t equal to 1, this approximation will not hold, because then the higher powers of t can't be neglected, right? Therefore, this thing will go to this this fixed terminal value, exponential convergence in the long run. And there are no turning points. You can see there is no maximum or minimum for this function here. And the transition from the linear behavior to the terminal behavior is occurring at capital T equal to 1. Below that, before that, you have a approximately linear growth. Beyond that, you'll have a convergence. That is incidentally the sort of thing you see. Let me just end on this point. I'll just give me a minute and I'll finish this thing. That is the sort of thing that you see in the real world. Things just don't keep growing forever and ever. Look at yourself. When you were a child, you were growing rapidly. But beyond the age of 15 or 16, your growth slowly converged towards a terminal value. So I don't think you will gain much in height or weight hereafter in your life. Maybe weight, but not height so much. So this is the formula that you have. There are no turning points. And at the transition, I'll just end on this point. At the transition, where t is equal to approximately equal to 1 upon b, the value of the function, when t is equal to approximately 1 upon b, small t is equal to 1 upon b, you'll have e raised to minus 1. So x is equal to x naught into 1 minus e raised to minus 1. So that will be equal to 0.63. So here is roughly around 60% or 63% of the total growth that is possible. You will have a transition from one behavior to other. So various physical systems can behave like that. Anyway, so I have finished the discussion of today. We have a lab on Monday. I will send you the link to the lab on Monday in the morning. Your batch list has not been finalized yet. I checked this morning. Well, I have to apologize probably for that on behalf of whoever is responsible, the authorities. So you'll just have to be a little patient. Monday's lecture will be Monday's lab. The link will be sent on Monday morning itself.